Let's take a look at the invert binary tree question from the Grind 75 list of problems. Given the root of a binary tree, invert the tree and return its root. So they've got an example here. So the root node is 4, and in the first input, or before it's inverted, its left node is a 2, its right node is a 7, and you can see in the result, the 7's now on the left, the 2 is on the right. And if we look down the tree, so if we look at, for example, originally the 2 had the 1 on the left and the 3 on the right, but if we look at the left, the output, it's just the opposite. Now the 3 is on the left and the 1 is on the right, and so same thing with from the 7 node, right? You have the 6 on the left and the 9 on the right, and here you've got the 9 on the left and the 6 on the right. They have another example that basically showcases it in a much more distilled manner. And then of course they've got an edge case here, which is, if you don't get a node, just return nothing. All right, so the constraints are the number of nodes in the tree is in the range of 0 to 100, and the values themselves are going to be from minus 100 to 100. All right, so it's not too tricky of a problem, but it can give you a little bit of grief if you're not entirely familiar with how you might approach this. So let's take a look at that. Okay, so the invert binary tree question is kind of a meme, and it's unlikely that you'll actually get it in an interview. However, you definitely might get something related to this or have to do this as part of like some other problem or something like that. So if you look at the actual sample input that they gave us, right? They gave us a 4, which has a left of 2 and a right of a 7, and the 2 has a left of a 1 and a right of a 3, and the 7 has a left of a 6 and a right of an 8. And we need to invert this. So how do we do that, right? So basically, if we just wanted to invert just the root node, which is the 4 initially, we want the left pointer, instead of pointing to the 2, we want that to point to the 7. And we want the right pointer, instead of pointing to the 7, we really want it to point to the 2. So we want to make sure also that whenever we're swapping those 2 pointers, that we have the entire tree inverted. So whenever we invert the left, we want to make sure that the left is inverted. And then whenever we invert the 2, for example, that this inverts down the chain to the right, or down the chain to the 1, and also this 2 will invert to the right, so on and so forth, right? We basically have to visit every node in the solution, which is why we get a time complexity O of n. And as far as space, because we're using recursion, or we're using a recursive solution, the snack space is actually going to be O of n as well. All right, so let's look at the code, and it's not too bad. All right, invert tree. So whenever we're thinking of recursive solutions, it's often better to avoid looking before you leap, as they call it. So it's what I mean by that is you want to handle your base cases so that you can comfortably write the code and have everything work the way you expect it, rather than write some code and before you trigger a recursive call, you're performing checks to make sure that you're not doing something incorrect. So the first thing that we'll see with this function is they give us an optional tree node for the root. So we might just do guard let root else return nil. And if you look at the actual tree node itself, there's really only 2 pointers, right? We have the left and we have the right. We don't actually need to be modifying the value of, we don't need to modify the val in tree node. We just need to update the pointers. Okay, so you might be looking at this code thinking, okay, well, it must just be, if I go root, or actually I think I need to go var here, right? So I can actually modify. If I go root dot left and I assign this to invert tree root dot right, and I go root dot right is equal to invert tree root dot left, and then I eventually just return my root. Is this the solution? Well, not quite. There's a few things that we kind of need to discuss here. So let's think about the recursive call, or the recursive calls that are happening. So the first time we get this function called, it's going to be called on the root node, and it's going to pass this check, right, to say, oh, do we actually have a node? Otherwise, we just return nil. That'll also handle cases down the chain where if we get to the lowest most nodes on our tree, it'll basically return a nil, which is exactly what you want. And with the root dot left, so what we're saying is we want to update our pointer to be whatever the inverted tree would be for the root.right. The problem here is that when you do this, you've lost your pointer to your original root.left because you're updating it at the same time. So whenever you get to line 22, whenever you're passing in root.left here, the problem is root.left has already been inverted and you're not pointing to the right thing at this point. So really what you need to do is keep a pointer, so you might call this original left, is equal to root.left. And now you'll have a working solution. And if you don't understand that, if you draw it out on paper or you were to pass this into debugger, you'll see what I'm talking about. You cannot modify something and then later refer to it because you've modified it already. You'll see this kind of pattern in many different kinds of problems where you need to hold on to an original pointer. You'll modify it and you'll use the old pointer in the future. And this is exactly the kind of problem that needs this kind of solution. So this is the recursive solution. So if I submit this, hoping it works, and it does work. All right, so thank you for this, watching this video. Hope you have a good day.